Welcome to Data Structures with Professor Califf. Today I'd like to talk about common collision handling techniques in hash tables. So collisions in hashing are when we have a hash function that maps multiple keys to the same location. More than will fit in the hash bucket. Sometimes we do have more than one spot in a given index, but this is the case where however many spots we have, we've had too many things go to the same place. There are two fundamental approaches for this. The first is called separate chaining, where we simply use a linked list. The second is called open addressing, where the idea is that I'm going to find a new location in the table. So first of all, I'd like to talk about the separate chaining approach. The idea is that the array locations are going to be pointers to linked lists where the nodes are going to contain the items. Insertion will add an item to the linked list, typically in front for efficiency. Search is going to check the linked list for the item. Deletion will simply remove the item from the linked list. Let's take a quick look at an example. I've got a hash table here of size 11 that has 4 items in it. We want to insert 15. 15 mod 11 is 4, so we're going to go to index 4 in our table and add that node to the front of the linked list. If we want to search for 18, 18 mod 11 is 7, so we go to that spot in the array and start looking through that linked list. And at the first item, we come to the 18, so we found it. Next, I'd like to look at searching for 37. So 37 mod 11 is 4. So we go to index 4 and start walking that linked list. 15 isn't it, 26 isn't it, 4 isn't it. And at this point, we're at the end of the linked list, so we know that 37 is not in the list. For our next example, I want to delete 26. Now 26 mod 11 is also 4. So we're going to go to index 4 and start searching the list. 15, not it. 26, we found it, so now we're simply going to remove it from that linked list. Looking at separate chaining, one advantage is that everything is in its intended hash bucket, so we're not having to wander around the table looking for things. We simply go to that spot, but then we do have to go through the linked list. This means that search and deletion can end up being big O of n, though insertion will always be big O of 1 as long as we insert at the beginning of the list. One disadvantage of separate chaining, besides potential poor performance if too many things are mapping to the same buckets, is unpredictable space use. Since not everything is contained within the fixed size array, we may not have a good idea of what amount of space we're going to need. Let's look now at the other approaches, the open addressing approaches. So the idea here is that everything is stored in the array. Different approaches are going to use different techniques for finding the new storage spot when the one they want is already taken. One of the challenges is that we have to know whether or not something is in a given spot. With the linked list, that's fairly straightforward. If there's a node, there's a thing. With the array, we have a spot at each location. Now, if we're storing something where we're using references or pointers, we can check for null. But in some cases, we're simply storing the thing itself, not a pointer to it. In that case, we'll typically use a flag indicating whether the spot is in use. First, I want to talk about linear open addressing because this is the simplest of these forms. It's also commonly known as linear probing. The basic concept is that when I get to a spot where I want to put an item, or I'm looking for an item, and there's something here, but it's not the one I'm looking for, I'm going to simply move to the next spot in the array, looping back to 0 as needed. So the math for that is going to be pretty straightforward. Current location is going to change to current location plus 1, mod the table size in order to wrap back around. So here we have our hash table as it would look with linear probing. We're assuming that we put the 4 in first, so the 26 will end up in the next spot. If we want to insert 15, again, we go to the 4. Can't insert it there because that spot is taken. We check the 5, that spot is also taken, so we move on to the 6 where we can actually put it in. Searching for 18, we're going to simply do the 18 mod 11, go to the 7. That is actually the item we're looking for, so we're done in that case. Searching for 37, we're going to start at the 4, move on 1 by 1 to the 26, the 15, the 18, and not until we get to 8 do we discover that it's not actually there. Deleting may look similar, so we're going to go to the 4 and then move on to the 26, and so then we could mark that not in use. But we have a problem here, and that is that if we mark the 5 as not in use, then we've lost track of the 15. So there are ways to deal with deletion in open addressing, despite the fact that removing an item can make us lose other items. Our solution, in general, is going to be logical deletion. Theoretically, we could move things around in the table, but we'll see that with some forms of open addressing in particular, you would have to go through the entire table to make sure that you had it set up so that you didn't have problems. The best thing to do is simply mark the item deleted. So the idea is we're going to use a 3-value flag instead of a 2-value flag. Empty, never used, will stop the search and allows us to insert. In use now, search will keep going unless this is the item, whether we're searching, inserting, or deleting. Deleted, search will keep going because we know something used to be here and it might have kept an item we're looking for from being put here. But we can go ahead and insert here. There's one other thing I'd like to make sure I point out about linear probing in particular. Suppose we want to insert the 16. So 16 mod 11 is 5. So we would start by looking at the 5 spot. Now, if we had actually deleted the 26, this would be open, but let's say we didn't. So we go and look at the 5, the 6, the 7. We can't actually insert until we get to index 8. This is an example of one of the problems that's very common with linear probing, though it's a danger with any form of open addressing. We have values that map to other indices, interfering with our ability to put things where they would go. Because we'd already put things that have index 4 into that spot at index 5 and the one at 6, we can't put the thing that goes to 5 in the table until we get down to 8. We refer to this as clumping. So looking at linear probing, everything is in the array, which can be very convenient. It's simple to compute. Linear probing is certainly one of the simplest of the options in terms of how do I find the place to put this? However, it is very prone to clumping. One attempt to try to reduce clumping is something called quadratic probing. The idea here is that we're going to have the first collision be 1 away still. But then with the second collision, instead of being the next item away, we're going to square the distance from the original hash index. So the second one would end up 4 away from the original hash index. The nth collision then is going to be n squared, so we would go to 9 away and then 16 away, 25 away, and so forth. The idea is that it's creating more of a gap between the items that are all going to the same place, so they're not all interfering with the same other indices. Now, computing quadratic probing is important to note some tricks of math. We could just say, here's the original hash index. Let's compute that squared index, how far we're away, the number of collisions we've had, and then add that to this original hash index, do the mod. However, that's inefficient because of the multiplication. Instead, we're going to simply use an offset from the current location so that our math ends up being much closer to linear probing math, with the difference that our offset is going to change. So initially the offset will be 1, but we're going to add 2 to it each time we have a collision. So we have current location gets current location plus the current offset, mod the table size. And the offset each time then gets increased by 2. So notice that the way math works, assuming we start with a current location of 0, just to simplify things. When we have 0 collisions, our offset is going to be 1 to find the first spot. So we add 1, which of course is the same result as linear probing. We've had 1 collision. We now increase our offset for the next collision to 3. So then if we need to go another step away, We go 3 more, which puts us 4 away from the original when we have had 2 collisions. We increase the offset to 5. 4 plus 5 is 9, so we're now 9 away from the original for the 3rd collision. Add 2 to 5. 7 plus 9 is 16. And this keeps working this way. 9 plus 16 is 25. 11 plus 25 is 36. And so if we look at this, we are in fact getting those squares from the original location by adding that next odd number to our current location. So let's look a little bit of examples. We're back with our hash table. It looks the same as the initial hash table for the linear probing case because the 26 just went 1 away. It was only 1 collision. So now if we insert the 15, again, 15 mod 11 is 4. So we first look 1 away, but now we need to look 3 more away for the next collision. So we end up putting the 15 in index 8. Searching for 18 is going to work exactly the same way. The 18 is still in its proper index. Searching for 37, we're going to look in the 4, then in the 5, then at index 8. Then we're going to move 5 more away, remembering to do our mod. So that will bring us to index 2, where we'll actually find that the 37 isn't there. So looking at quadratic probing as an option, computations are really not much worse than linear probing if we do it the efficient way. We reduce the clumping and the interference with other items. So if we wanted to put 16 in for our example, we actually have a spot at 6. Maybe not the spot at 5, but it's closer. It's only 1 step away. So we're better off than we were in the linear probing case. Note that logical deletion is even more important than it was with linear probing, because it would be even harder to go try to figure out which things should be moved to come fill this in. Despite the improvements over linear probing, operations can still end up being big O of n, particularly in pathological cases or with poor table sizes. So that leads us to our last option of the 4 we're going to talk about in this video, and that's double hashing. So the goal here is to try to create scatter after a collision. Try to keep us from having to go check all of the other slots that belong to this index. With linear probing, with quadratic probing, it's very consistent which places we go given a starting index. We want to change that. Basically, we want values that map to the same hash index to get different offsets. We're going to do that by using a second hash function to compute that offset. So the way we do that is we're going to use a prime that is smaller than table size, usually the next prime down from the table size. We're going to use mod, but we do need to prevent 0 from being a value we end up with, because adding 0 to something just gives us the same thing, not a very effective offset. So what we're going to do is we're going to either add 1 to the result or subtract the result from the prime. That will give us something in the range from 1 to that prime number, which should work well for us. Very, very important. This is the single biggest mistake that my students make. The second hash function computes an offset, not a location. So we're not coming up with something where we have 2 different places to go. We're coming up with, okay, this was the starting location. Now, here's how we find locations until we find one that is open or the one that holds the value if we're searching. So let's see what this looks like. We do need to start with just the 12, 4, and 18 in the table and go ahead and insert the 26 because it's not going to end up at the 5. So when I go to insert the 26, I'm going to do 26 mod 11 is still 4. But I need to now compute my other function, and I'm going to use mod 7 and then plus 1 to get my offset. So 26 mod 7 is 5. We add 1 to that to get 6 to ensure that we don't have a 0 for anything. And so we're going to go to 10. That's open, so we insert the 26 in at the 10. Now I want to go ahead and insert the 15. 15 mod 11 is 4. So we now compute 15 mod 7 plus 1. 15 mod 7 is 1, plus 1 is 2. So we're going to move by 2 each time and put the 15 in the 6. So notice the 15 and the 26 didn't have anything to do with each other. And that's the beauty of double hashing. Now, when we go to search for 37, obviously I'm skipping searching for 18 because it's going to work exactly the same way as it did for the last two. Searching for 37, once again, we have 37 mod 11 is 4, and we compute 37 mod 7 is 2, plus 1 is 3. So now our offset is 3. We're going to check each of these spots. So first we check the 7. It has something in it that isn't 37, so we need to keep going. The 10 has something in it that isn't 37, so again we need to keep going. And not until we get to the 2 will we discover that we have an open spot and 37 isn't in our table. So this is not perfect. We're not going to avoid having to look at other items, but it is generally better than linear probing for sure, and then quadratic probing in many cases. This tends to have the best performance out of the 4 techniques. Logical deletion is absolutely necessary. We would have to look at the entire table to try to fix something after a deletion if we didn't use logical deletion. Keys to good performance with double hashing are the table size being prime. That's important for all of these. And the table being less than half full. So thank you for watching. The next video, I'm going to talk about what we do about that issue that we need for the table size to stay big enough. So as we're adding things, what are we going to do when the table gets too full?